Okay, so yeah. Oh, sorry. I think we just got a message in the chat. I just want to check that first.
Nick's having problems with it. I'll message him.
Okay. Well, I guess we can start in the meantime only because what we want to start with is we want to figure out uh, where is everyone kind of struggling with, like where's everyone at, what is your like biggest challenge at the moment. um, I hope you guys don't mind if since it's just three of you, if we just kind of go in order. If there's nothing that you want to talk about, there's nothing that you want to focus on, nothing you're struggling with, um, that's fine too. But uh, without further ado, Olajide, is there anything currently you are having difficulties with, or anything you would like to like focus on and talk about?
Um, for now, I'm not really having any issues because I'm kind of like getting familiar with everything like
Okay.
properly. So if I have any questions at all, I'm going to.
Like, I guess a second way to ask that question is like, are you interested in the theory or the application side of things right now? We're trying to get a gauge of like where people are at with learning this.
And this is fully like for us to kind of like understand like are we doing well with how we are training, and trying to help you guys get better. Um, so yeah, so I take it like Olajide, you're more looking at the learning materials right now, like just like going through the reading. Um, oh, Enoch. Oh yeah, perfect timing. I was just about to ask you next. Um,
Yeah, hi.
hey.
Yes, so personally, I had an issue with the third project. I had an issue with mix. So yeah, so it took me quite some time to resolve the issues I had, and apart from that, I've not had any major issue.
Well,
Apart from
if Nix
yeah,
is your only issue so far, then that makes you a true Haskell developer because all of us Haskellers have issues with Nix at some point.
Yeah.
But it's great that it like when it works like
yeah.
forever. But yeah, it can be tricky sometimes.
The
So glad you
setup
figured it
is,
out.
yeah.
Yeah, the setup of it can be tricky.
Uh, just pour my coffee here. Don't mind me. Um, okay. So yeah, no, and especially too with if any of you guys uh, with the challenge that Enoch ran into, I think it highlights like a great question to ask. If you for any reason need to like reinstall Nix, let us know, and like honestly, we'll just like hop on a call with you, like because that can be really difficult. Like Nix is not well set up to reinstall. That's just one of the downsides of it. But like once you have either installed, once like the way you should the first time, or have it installed like and reset up, it like works perfectly, like Kyle was saying. Um, and also too, I want to like further like incentivize you guys, or like why would you like kind of tell us like where you're struggling. um and like like I get like no one wants to say like, oh, like I it's not like anyone's favorite thing to say or whatever. And I know we have more people on the call now, so it might even be more intimidating. That's always going to be true. but like one of the last companies I worked at, you know, it was very important to be as fast as possible, right? And I'm sure you guys want to get a job as fast as possible. And there's a lot of cases that I found where I didn't need to ask a question. And at first in the company, I was not asking any questions because I was like, I'm independent. You know, I don't need help. I can do this on my own. But what I found is that like in asking a certain amount of questions, at least like a bare minimum amount of questions, um, it allowed me to kind of like move just way faster. Because ultimately, what you're trying to do in any case, like if you let's say you're trying to write something, you get stuck. What's happening when you're stuck on something is that you don't know the answer, right? You're trying to figure out like what is the solution to this problem that I'm facing, where are things going wrong, and there's so much to like unfold about that situation, and more likely than not, someone has has figured that out before, and so like it's great to have that individual skill, and we really want to encourage that too. Like it's like we want to do both. We want to encourage you to ask questions, but we want to be able to ask you or encourage you to sort of problem solve and figure out like where you're getting stuck on your own, because that's really important too. In the case of no one having an answer to your question, but like when you go into a company and um, you know, there is a case where you could solve the problem yourself, but someone also knows how to solve that problem. Not 10 times out of 10. Kyle maybe disagree with me here if it's like 9 out of 10. I think maybe it's less, but I would say like 10 times out of
Probably
10.
9.5,
9.5 times out of 10.
maybe
Yeah,
9.6.
not yeah, right. There's like
They're
there's
just
there's the odd case. There's the odd case where it's like, bro, like I'm busy. Like, can you figure this out on your own? But 9 times out of 10, it's like they won't even say I'm busy because it's like, oh well, yeah, you just gotta do this. Like in one sentence, like someone can solve your problem that would take you 5 days to figure out on your own.
yeah, this is a really good point. If I might jump in, most teams actually have a rule put in place where if you've gone an hour stuck on a problem, you have to reach out to the team. And this is because, well, I mean, usually this is like everyone kind of agrees that it's a good idea, but it's in the best interest of the company to not have someone working on the same problem for 2 days, right? Um, so we have a rule actually at our job where if you're stuck problem solving for more than an hour, you have I mean not have to, but you're supposed to ask a question in the team chat, and then if anyone has an answer, then they'll help you out. Or if anyone wants to jump on a call, then they'll help you out. It's very much like a team. It's a team sport in that regard. So any practice you can get doing that before you go to the job is going to be extremely helpful. So like if you're stuck on something for more than an hour, like please reach out.
Mhm. And yeah, and like even just to put that further into an example, like one of the last companies I was working at was like a blockchain company, and they worked with all different types of blockchains, um, and you know, it's interesting because like what I've learned through that specific uh, you know category of jobs is that like you'll just be working on a blockchain sometimes that has like horrible documentation, and that's not your fault. But like it's something you have to deal with. Hopefully, you don't have to deal with it, but like there's just going to be a lot of times where you are dealing with horrible documentation, and the only way to like really figure it out without like doing like some sort of grassroots analysis, like some sort of deep analysis, is just to ask a question. Um, so that's not the case here with Haskell. Kyle, I see you laughing, or I feel like a story
No,
here.
sorry, someone else in the room. My
Oh,
bad.
yeah, all good, all good. Um, Luna the pop's pretty funny, eh? But
Luna's funny.
yeah. Um, but yeah, no. So I hope that motivates you guys to ask questions. Yeah, again, here I'll admit that definitely like it's sort of self motivated that we would love to know like where you guys are at, like how are you finding the material, and what can we do to make Ace better, because we're still very much in the early stages, and we need to grow ourselves. So, but yeah, now that we have more people in the room, would anyone like to like volunteer? Like, it doesn't even have to be something you're struggling with, but like, what do you think we should talk about today? We have a lesson plan in place. It's like very beginner focused, lesson plan today. We're gonna be switching gears from like doing like a project in the session to just doing like what's the basics of Haskell, um, and so it will kind of cross over with some of the earlier chapters. But yeah, does anyone have like a request for what we should talk about today? You can put it in the chat
You can
too.
say it out loud, yeah, or
Yeah.
put it in the chat.
Interesting. Um, I would love to talk about this. We could, all it's not super beginner focused. I mean, it might be like
I mean, talking about monads might be a good, like, even if you can just do it for 10, 15
okay,
minutes, right? Like,
okay,
and then we can get to some of the other stuff. But I was even thinking that, like, we should kind of demystify this whole monad thing, right? So the more that people work with them, the better.
okay, fair enough. And I think state monad would be a good one. Um, I haven't used IORef a ton. I have seen it in practice, but yeah, okay. Here's what I'm thinking. We'll do the beginner lesson, and we'll tie in state monad, at the end of new types. Kyle, if you could remember that for me, if I get going too fast. Yeah,
Sounds good.
and then um, at any point during the lesson, there's no deadline to say when you would what you would like to focus on. Even if there's something in the lesson that I'm focused on, and you're saying like, what are you talking about? What is this word? Just like please let me know, and we'll dig into it deeper. So without further ado, I'm gonna open up my Emacs. Okay. Yeah, we'll just use this. So, I'm just in this. I'm just gonna use like a project to run stuff. The demo we did in week 1. So if you guys don't remember that, it's just like a credit card app, or like a store app which takes a credit card and all that. Not super important, but I just want to use it so that I can do Cabal REPL here, and I need to get that in my path. Oh, I'm gonna need GHC as well. This is just me. This is just how I use Nix. You don't have to worry about this so much. All that matters is that now I can use GHC, as I couldn't before, and same with Cabal. So I'm going to do Cabal REPL. I'm going to get my lesson plan out in front of me. Okay, so the lesson plan for today is ultimately, so we're going to go through data types. And so the data types that we're going to go through is we're going to talk about the types that exist in other languages. We're going to talk about the different types of keywords that exist for making data structures in Haskell. So our we want to expand on the basics of having like integer and character and string that are in other languages, and we're going to do that through data, new type, and type to model our model our domain. And then after that, we're going to see how do we actually use types, and we use types through functions. I like to think of data types as like a state, and a function as something that changes this state into something else, into a state 2. And we're through functions, we're going to look at ways to pattern match. We're going to get into what does it mean to pattern match, and how does this relate to data types. And we're going to look at like the actual specific ways, which is in the function head. In case statements, and lastly through our more expressive way of in guards. And then lastly, we're going to expand on our idea of functions by looking at the concept of overloaded functions. And so all overloaded functions means, and we'll get to this more in depth later, is a function that I don't know if I'm using the correct terminology here, and correct me if I'm wrong, Kyle. But ultimately, it just works for more than one case. Yeah, and we'll see what
You're
that
talking
means.
about type classes?
Yes.
I would think it's not really an overloaded function. Because, well, at least not in the traditional sense. Like overloaded functions in object-oriented programming are from abstract classes. So it's like, well, I guess, okay,
It is
maybe,
definitely an
yeah.
overloaded function. I mean,
No, now that, yeah, I correct myself, yeah. But the type class itself functions more as the interface, whereas you're going to be defining overloaded functions for that interface.
the goal of them though is like to overload. You know what?
Yeah.
We'll just come back to this.
We'll get to
Yeah.
that. It is. Yeah.
You're right. You're right that like overloaded and object-oriented sense does mean like we are talking about something very different. The key point to note here is that these are absolutely not OOP classes.
Yeah. Type classes themselves function like interfaces, but they're different. So we'll get into that.
So
Like you'd use them in the same kind of place you'd use an interface, but they're a lot more powerful. So go ahead.
So like I'm just gonna like list out like our this again like a very basic introductory lesson. So I just want to list out like what types do we have in Haskell that exist in other languages. So the first one that comes to mind is we have character, we have int or integer. Both of these are very similar. We have a string. We have a tuple, right? So we can have like what we could have whatever in the tuple. So I'm just gonna put A and B. We have a list, so we can have like a list of something. So list of some type. And these A and B, just to note that these can be whatever type, and so that aspect is Haskell. But I mean, in JavaScript or other languages, you can have A and B be any types as well, right? So we could have like, for example, and or even further, just like I'm a string 1. And technically speaking, this is remind me here is that we have maps in Haskell, right? So we can have a map of like string to integer, just like we can in JavaScript. What else is in basic languages that am I forgetting any? I don't think I am.
I mean, most languages have like a lot of different kind of types defined, like in their, might not be directly at like primitive types. 'Cause, like
Primitives, yeah.
for here you have like, I guess in Haskell, map is kind of a primitive, but actually I think no, map comes from data, doesn't it?
Or from containers, yeah.
Containers. So it's kind of similar, right? Like in for example, in C sharp, system.collections has a bunch of these. So there are a lot of shared types, but with Haskell, I guess the big difference in functional programming in general is that the type system expands beyond the primitive types. So like a lot of this stuff that you can do at the type level is actually like as if you're creating new primitive types, where in object oriented you're creating classes that wrap primitive types.
Right. So we might have something like class person, where this is gonna make it annoying. Class person where we have like age, and we set we would set their age. This is not like this is just pseudocode here. We set their age to being like 20. We set their name to being Galen. I'm not 20. I don't know why I picked 20. And we would have essentially this like this struct or this object which has a number of fields, which are just ultimately basic data types. And then we might have like in a class you can have like change name, and this is just a function, right? So, what is it in Java or JavaScript? It'd be like.
I love how you're even writing it in a functional manner.
I know. I'm doing like a horrible like in between.
Because you're using a lambda in JavaScript, which is good. You can, but this goes to show you that like you can write functionally in JavaScript, and you should if you use JavaScript.
Right. And you would do something like self.name equals new name, and all this stuff, and this is how you would. This is like almost like also a basic lesson of like how you would represent complex data in object-oriented programming, right? And we would just have any object slash class would ultimately just be a a record with a number of primitive data types, and then maybe some functions to change these fields. So that's that. I don't think there's anything more to say about that. Of course.
You missed Boolean.
Oh yeah, right. We have
That was
Boolean. Oh my
every day.
gosh. Right. Can't forget about that. Probably truly the most important. No, I'm kidding. But trying to make a bad pun. Yeah. But same thing, right? So we can have just a it is happy equals true. Very happy. And that would be a Boolean. And again, so just like that's how we do that. And we would have like in object-oriented classes, like we could make person into an abstract class, but anyways, enough about object-oriented. That's not why we're here. So how do we how did these look in Haskell? A lot of these are handled by the compiler. Like for example, a list. If you like look up a list on Google, you can't find it, which I find peculiar to this day. So like that's one odd thing. You can look up like a map. You can see like data containers. Oh, like module data.map. Here's the actual data type in containers, and you can look that up. As for Boolean, how would a Boolean be represented in Haskell? Like, if we were to look up this code on Google, we looked up Boolean, we can find it here. Oh, interesting. Oh, sorry. Sorry. I'm getting confused. The concept of I believe in JavaScript it's called a Boolean, right?
No, it's in Java. That's where it came from.
Okay,
Boolean.
yeah. So whereas in Haskell it's just a bool, and we could click on this, we could look it up or whatever. But I just happen to know that the way in which data, the Boolean, or sorry, bool, I'm going to change this now to not mess me up, is defined exactly like this. This is the actual source code where bool comes into existence. Is just simply true, false. And so this is this is really as simple as data constructors get. Is ultimately, I mean, we could make it even simpler here, for sure. But ultimately, what this means is that like this like little bar here just means like almost like or. Like a bool can be either true or false. Is how I read it. And we would just use this to like separate like out like cases. So like let's say we are crazy and we want to be like JavaScript, and we also want to have a null. Then we could in theory add it to our boolean.
Nice jab.
Thank you. Thank you. I saw this. I saw this like meme. It was like. Truth-ish or like truth, where it was like
Yeah, truth-ish.
There's like undefined. I don't know, like true-ish. Yeah, true-ish or whatever. So we could, we literally could say I don't want to use bool. I want to use my boolie, and then add on to it this way if we want to make our own. But Haskell has already made it. So like again, if we look into the source code here, there's nothing crazy that's going on. It's literally just these exact characters. Where is it? I guess like, well, that's like whatever. That you can ignore that. But ultimately, what's going on here is that we just have this exact code here defines a boolean, and that goes for the rest of what we're doing here. The point being that it's very easy to add on to the data types that are in Haskell, and that's true for some other languages, but not always the case. But what this means is that it allows us to think very clearly about states, right? So like, we talked about like state in past lessons or whatever, and like state is like an interesting. It's an overloaded term. It means a lot of different things depending on what we're talking about here. But I think if we were to take away all of the chaos that is object-oriented programming, and other things like that. And if we had never, like, this is how I originally thought about state as a someone who learned functional programming first-ish. That's true-ish, I suppose, because I did learn Python first, but I became a master in Haskell before I became a master in Python. But I like to think of state as like just like the transition between like functions. So like, for example, like let's say our input state, right? Our x is false. and if we were to then say y as like our output, and we put not x, then our second state, we would know at this point in time is is true. If we were to say I guess y2, and we said not y, and we kept doing this, we know that it's just simply flipping back and forth from true to false. But like the point being here is that at any point in time, we can easily know the value of, we can easily reason about the value of y3. We know that y3 is equal to, well, let me think this through. Y is equal to true. So that would mean that y is equal to false, which means this is equal to true. And like, no matter how complicated the data types that we use, or how complicated the functions get, we can just easily continue to look at our Haskell code, and if we really want to reason about it, we can. You don't always, like, it's not like you actually have to, but you definitely can. And the reason you would want to is if you're getting a unexpected value, or you have a bug, so to speak. Because we've avoided type errors in Haskell, but we can still have value errors in Haskell. Like, let's say for example, I just simply forgot to apply not here. I would be like confused as to why I'm expecting true here, but it's actually is false. So yeah, that's the core of it, and we'll like keep that in mind as we get into more complicated pieces here. But anyways, so that's bool, and so we can continue to use this data declaration keyword for anything else, right? So like, let's say we wanted to say, instructors. Data instructors for ACE is Lauren, Kyle, Galen, right? And yeah, that's another way we could define it. We can also do one more thing, which is we could give them possession of something. So like, what could this be? Like, and this is like a, like, I don't know the actual
Our favorite data type.
Our favorite data type. Yeah, favorite data type. Now keep in mind, I don't have to type out full favorite data type. I could just, instead of saying full favorite data type, I could have just put like the letter F or the letter A. The only thing that matters is that it starts with a lowercase character. And that's important to note with data types in Haskell, is that like, this is not valid, but this is valid. And so anytime you see something that is uppercase, it's a data type, right? There are some very few exceptions to that, like, and we'll see what those are, but by and large, if you see an uppercase word or string in your code, it's a data type. And same with functions, as we'll see. The F here would definitely be a data type, and then F would not be a data type. That, like, this would just be invalid syntax if we said something like int to int. That does not make sense, but this makes sense. Anyways, so we give them their favorite data type, and I'm going to put them on a new line here, and we're going to say favorite data type. It's a lot of typing. But let in the case of favorite data type, this assumes that this implicitly assumes that we all have the same data type, the same favorite data type. So let's do something else actually. So if we want to allow each person to have their own favorite data type, we're gonna add more variables to this data declaration. So we're gonna say LKG just to denote, who this applies to. And so we're gonna say Lauren L, Kyle K, Galen G. And then we can do something like we could have like, for example, like what does this actually mean in practice? We could have a list that looks like Lauren, car, Lauren loves her cars, Kyle, Boole, because he loves to be true, and Galen, I don't know. What would I pick? Integer, because I love math. And that would, sorry, I'm stupid. This would be an actual Haskell value here, right? So we could say our faves is a list, and then if we reason from there, if we reason from like what our value is, and this is also something that the Haskell compiler will do too. This is still not valid. I'm just realizing. I kind of put like fill in the blanks almost here. So I've said to myself that like Lauren loves characters, but I need to put an actual character there, not the character data type. That doesn't make any sense, right? You wouldn't say like in JavaScript like I'm gonna add an int plus an int. You would like say like I'm gonna add 2 plus 3. So you would add like a case of that data type. So a case of character is L, and then bool would be true, and then I'm going to use the number 5 because that is my favorite number. Yeah, and I'm not going to argue with myself about that. There's a lot of great numbers out there, but and so next question we want to know, like, so we have defined a valid value here, and we don't we don't actually for sure have to do this, but like let's say we wanted to figure out like what is the type signature here, what is the type of this value. So like there's two, like this is really cool. We could figure it out on our own. We have all the pieces here to reason about it. However, we can also just use the Haskell compiler. So I'm going to use a type tool here. And if you're using Visual Studio Code or you have Haskell Language Server installed, then this will tell you the same thing. But let's say I reload. The heck? I'm not, sorry, my bad. I'm not in.
I believe you need.
Yeah, I went too far into the.
Did you specify a main module at the top of this, or do you not need to? Oh, you did. Yeah, you're good.
Why is that? Okay. Okay, well, this is strange. Let me just. Okay. No, this should work. I don't know why that happened, but we didn't really get that far here, so I'm just going to copy this into a fresh project here. I don't know why I did that, to be honest, because it's not that hard to make a new project. I'm incredibly lazy. One downside to Haskell is that once you do Haskell, you think that you are it's good to be lazy, which is only true if it's code. Okay, so I removed the bool here because it's saying and you know what? Today I'm going to make sure that I go through every single error that we do, assuming it's the first time we've seen the error today. And this one's really simple. Ambiguous occurrence, true. It could refer to prelude.true or main.true. So main.true means like it's the definition of true coming from the module main, which is my module here. Or it's from the prelude module, which is just like the default Haskell module. Right, and we can look this up if you want. Again, if you want to learn more about this, we're actually here. If we find bool, we see that it's in the prelude module. The second one that we come across is an error I purposely caused is the type wildcard, and this is cool because the Haskell compiler knows what the data type we have here is. So we're gonna first put this in, and we're gonna see instructors. It's a list of the data type, which is in the data type being instructors, car, bool, integer. Cool. Okay, so the reason for this is because instructors is a data type which takes 3 other data types as arguments to create a variation of data types, right? So like I can give it that car, bool, and integer, and that will slot these in here and say, okay, the L goes here, the K goes here, the G goes here. So Galen is an integer. That makes sense. So that would apply to G, and voila, right? So like from the value level, I've given a 5. It knows that a 5 is of the type, and I could test this too. And what I would see is that this is an integer. It knows that 5 is an integer. That's very simple to do. Hopefully it knows it's an integer. That's nothing special. But then that must mean that the G here is integer. And then the same thing is true for bool and car. So yeah. And that's what creates this instructor's car bool integer. Now let's say you know Lauren, Kyle, and I make up our minds, and we are like, okay, you know what? I know for sure that my favorite type is this. We don't have to have these in the function head either. We could instead say car and Kyle bool and Galen integer. Right, and so we could keep this here, but for the sake of like simplicity, we don't need them here. It's still valid code, sure, but like, what's the point of like, you know, it's like having a function that takes an argument but then never uses it, right? Why would we do that? So let's just get rid of them, and now we can see that this data type is going to change, and this is going to complain, because now it's saying expected a kind of data type that is like this, but we found something that's like, so we haven't gotten to kinds yet. Ultimately, what happens here is, in order, we can't break this down yet, right? So let's step away from this, and if we had instructors here, instructors as it is currently defined is of the kind star, right? That's the notation for it, is of the kind star. If we add in, let's say Lauren's favorite data type here, and we are going to continue to apply it, then what we see is that the kind is star to star, right? So we'll get into functions later, but this is everything in Haskell. Like you'll realize is just a function. Like everything is just a function. Even like the way the language is defined is just a function. And like what we would see here with like a function called f is that we would have int to string. We're going to convert some integer to a string. We would just see that we would know by reading this type signature that this just means it takes one argument, which happens to be of the type int. Now, in the case of kinds here, this is just more generic. So we can give any data type and it will work, right? So like, let's say we did this and I said instructor's car, this would now function properly, right? Because Kyle still loves bool, Galen still loves integer, Lauren isn't sure about car, but currently likes car. So that's why we have our instructor's data type still taking one argument, and this will now compile, except for the fact that this is not even valid syntax there. Let me just get rid of that. And so voila, now we can see that compiles. So if we were to then build back up to where we were, we would see that Kyle, and I'm going to change it to a B here for bool. Kyle also not being sure about his favorite data type means that now we have two arguments to become a concrete type, right? That's a key piece of terminology. It's just like a concrete type. It's just like a nice way to think about like what we are doing, and I'll use that terminology quite a lot, like because instructors, like this piece here is not itself a concrete type, but something that creates concrete types, right? So like by nature of this being a higher kinded data type, this means that L can be anything and B can be anything, as long as it's a valid Haskell type. So yeah.
This, by the way, just figured I'd chime in here for a second. What you're seeing here is actually not supported by any other compiler except I think Rust has this concept, but that's because Rust was written in Haskell. So yeah, like this whole idea of higher kinded types is quite new, and it allows us to do a lot at the type level. Like you can quite literally, like there's like full programs that just operate at the type level, right? And it's extremely powerful. So the more you use this, I think the more you'll see, like it's a great way to write libraries. It's a great way to write reusable abstract functions and stuff like that using these kinds of types.
And a great example of that is something we've already seen, is servant. We use servant in, I believe, lesson 2. We didn't get too deep into it. We weren't talking about the data types of servant, but servant ultimately just says, HTTP is a protocol. It has a very specific format, and so we're just going to typify that format, right? And so we have basic concrete things like headers are in every single HTTP request, right? There's anywhere from, I guess, in theory 0 headers to I don't know if there's a limit on headers, but there's some amount of headers, and then we have a function body, which can be anything, and so servant allows us to work with that basic specification to say what we should expect in an HTTP request. So for example, we can say that a header should have a value that is of a very specific type, and if it is not of that type, then reject it, right? So you know, I'm trying to remember, upgrade insecure connections would be of the type Boolean, and so if it sees that upgrade insecure connections for whatever reason, like maybe it's like an attack or something, is like a string that's like you know like hello, or for some reason I don't know what kind of attack this is, then it would just reject the request. Um, and so what this means is that what it means for us as you know, of servants to servant, like right, we're just like the people who haven't written servant but like know how to work with it, is that we can just use servant to ensure that we were getting a boolean and then work with that assumption, so to speak, right? So that like if we were to write a function that looks at like the upgrade insecure requests, we could literally just say it's just it's a bool, and I do some action with it. I do some IO action with it, and I don't ever have to think about, because of servant, I know it's going to be a bool, and because of Haskell and the Haskell type system, I know that I can write a function which takes that bool and does something with it, and then I have in that code written bulletproof code that will never fail if my defensive parsing is not as it's not perfect, right? So like you know, in JavaScript, right, we would just be saying you know, like we might have like our HTTP request is like an object, and we would just say like HTTP request dot upgrade, you know, equals like, you know, we had two different types of equals here, which is crazy to begin with. Equals true, right? Because ultimately at first it would be a string, and I guess we have two types of string in JavaScript. But like, let's say for whatever reason, you know, like a hacker, like, I don't know, like just does like true, or I guess like in, you know, it does the opposite of what we're expecting, then our defensive parsing would fail, and our, you know, that would not be good. But since we have types, we don't need to worry about that. And sorry, that's a bit of a tangent. But yeah.
Awesome.
And so anyway,
Just a-
so oh yeah.
Just a time check. We're an hour in, so
Time check. Yeah, fair enough. So the last thing is like, so how we got to this expected kind here. I don't think I need to change this anymore for us to think about the next piece here. I will in a second, but if we look at this now, we see 1, 2, 3, 4 stars, right? We see 1, 2 in a function signature, and we know that, you know, you know, if we see this, that there's one argument here, we know for the same reason that before the last arrow, we could count the number of you know, stars here and see how many arguments that that function or that type constructor takes. So here we can see that instructors takes 3 types, which makes so much sense because that's literally exactly what we did. So, right, so that would be what we had before, and we can again see that this takes 3 types. So that's the system here. But yeah, so now let's go back to where we were, and we yeah. So Lauren still was able to pick her own favorite data type, whereas Kyle and I had statically picked types. So mine was integer, and this would now type check. So I'm just gonna put this here. So that works. Okay. like that's the core of data types. We still have newtype and type to talk about, but like the core conceptual information that exists about data types is really represented in the data keyword. What we'll see is that like newtype and type are like almost like I want to call them like dumber versions of data. That's not exactly true, but like they're much simpler to use and think about than data. Data, right? Data allows us to have multiple cases, and that's really the key difference here. So let's say like instructors v2. So like Lauren looks at this lesson and she's like, "Man, Galen, you suck at coding. Like you have no idea what you're talking about. I hate you," and that's fair. You know what? I'm still happy according to our we got rid of the constructor data or the object oriented version. But Lauren says that like I am the only instructor now. Kyle and Galen, you're both fired. So we could represent that very easily by doing that. And instructors v2 is just Lauren. I'm going to say Lauren v2 because, you know, with cutting the crappy instructors out, Lauren has become an even better instructor herself. And so now we don't, so that story said and done, we don't need this data declaration anymore. And so instead, we could, in theory, just use newtype, right? And the reason for this is because there's only one case. And so, like, you might be like thinking, like, where do we ever want this? But ultimately, like, I think the most common case for it is when we see monads. There's a lot of like monad transformers that use newtype, and we'll get into monad transformers. But if you don't know what that means, that's not a problem in the slightest. We will talk about state T at a certain point, but and that's how we'll come back to that. And also the last thing I should say about newtype is that it can also take any number of data types, right? So Lauren could take, you know, a T for a type. I'm going to correct that, and a S for a salary, and then you know, and we can continue adding on what these are or whatever, and we could also say that like you know. And like let's say like this is salary or whatever, again just to like really make this like a storyline here, there's only like one logical way to represent a salary, which is through a number, and there's many there's many different number types, but like let's assume that there's only one, and that's integer. Oh, and this was reminding me actually, I guess technically, oh, did we I am just going to copy this in here. Where was I? I was realizing we missed a data type. Oh, and I guess there's also, in addition to integer, there's also float in other languages. Or float or double. Very similar, depending on what the language is, but I believe a lot also have both, depending on the particular use case. And so anyways, and now that we know that, let's actually just use double instead. And double, you know, makes sense because currency, for the most part, you know, at least fiat currency has 2 decimal places. So having a double, and double just means like a number like 1.0 or 1.01, in case you're not familiar with it. But that's how we now define instructors v2, right? And we'll still see. Oh, sorry, I don't know why I did this. This is definitely not valid code. And let's say I type this in here. It's saying unexpected type, right? I'm giving it a type where it's expecting a variable. And so like let's say I was to like put here instead a D, then that would make sense. That would be valid, but I am trying to change this so that it's statically defined to being a double, right? I don't need the type to be changing. That's not going to be very good for the payroll system. So yeah. But Lauren still wants to have a favorite type. Oh, and actually, I'm mistaken here. So like, I guess I can't do that. That is true. It's saying a constructor of a new type. The constructor keyword here of a new type must have exactly one field. But Lauren v2 has two. And the reason for that is that like, it's like, types have fields, and we could define this like another way, which might be a little bit more familiar to people. And we could say that the T is like, I don't know, the variable name favorite type is of the type T, whatever that is, and then salary type is double. This is not valid. It would be valid if we use data type here, or sorry, data keyword here. But specifically for new types, we can only have one field. So we could have something like this, and then we could have like, for example, we I don't know if I should get it. If you don't understand this next part, that's totally fine. Don't worry about it. But I'm gonna say, let's say we have like, for the sake of showing multiple variables in the function or in the type constructor head, we have this complex type, and complex looks like that. That would be one way in which we could have a new type with multiple variables in the function head, just to show it's possible. And so, like for example, complex here could just simply be a list, right? So like it could be a list, and the list would ultimately just be like, if this is a list and this is a integer, then it would just be a list of int. And so if you don't understand that, again, do not worry about that even slightly. So that wraps it up for new type. What is type? Type just simply means that this is just a new name. So, for example, if I don't like the name bool, I could simply say type booly equals bool. And then now I can write my functions here, with I could change this out here to being booly, and it would not change the meaning of it, the underlying meaning of it whatsoever. It would just change like what I see. So that's that. And an actual real example of this is string. So string is defined as a list of car, right? And so we can literally like look this up in our REPL here. If we say information on string, we see that the definition of it is type string equals list of car, and that's that. Does anyone have any questions on that? On anything we covered so far with data types? It will be important for the next piece. So if you do have a question, like you definitely should ask it, because there's a good chance that if you don't understand what we talked about here, you're not going to understand the next piece.
What's the next piece?
What's the next piece? Thank you for asking. That's a good question. Okay, so now we'll move on to functions. And all that functions are how one way to think about functions, and the way that I think about functions, is that they are just something that takes some input data type, does some logic, or just some application of other functions, which ultimately just boil down to logic, and then return some new data type. And so, thanks to Haskell and our type signatures, it's very easy to reason about what the input and output is. So, for example, let's say I have a let's say I have I'm gonna go back to this just for the sake of it. I think, yeah, this is what I'm gonna do. So I'm gonna go back to this. I'm gonna say LBI. So I gotta change this to update it, or to keep the code being correct here. Otherwise, it's gonna complain. And so I want to go from an instructor's car bool integer to I want to flip around Kyle, Lauren, and I are going to trade types. So let's say, what's the output here? Let's just say in random order, integer car bool. Right, and I just made that up, but even though I just made that up, or kind of made that very arbitrary, there's this means a very specific thing to the Haskell compiler. And I'm not going to get into this yet because I do want to return to this. But ultimately, this means that I have some input and some output. And the output is going to be of the type instructors. I'm just going to copy paste. Instructors integer car bool, and the input is going to be of the type and that might already be obvious to you if you know Haskell, but ultimately the point I'm making here is that and it might not be super clear, but you don't need to use return. There's no need for return in Haskell. You might see in certain cases, in our examples, that we use the keyword return, or sorry, the function return. But that's a very particular thing. And actually, you don't need return in the context of a normal function here. So, pretend you never saw those returns, and you'll start to see returns on your thinking. No, but you just pretend you never saw that. You don't need to do that, right? So a simpler example is let's say I have a function here of int to int, and I have some x input. I could just do this. In order to satisfy the function, the function's type signature, I can just do this. I don't need in object oriented, you would need to say return x, but you don't need to. So all that has to happen to the right of this function is that you are just writing an expression which evaluates down to that type. Right, that's it. So there's no need to say return because Haskell is just simply better than needing some sort of return keyword. And yeah, that's how I'll explain it. I don't know if you want to explain that another way, Kyle, but that's how I'll explain it. You just don't need the concept of return is only because of some of the complexities of object-oriented programming, whereas we can just say, here's an expression that evaluates to being this type.
Yeah, I mean, even in object-oriented programming, they're removing the return keyword in a lot of cases. You just don't need it.
Oh, interesting.
Yeah, I think it's Go doesn't use return. It's just the final, the final. It's either Go or Rust, I forget. But one of those two, it doesn't use return. It's just whatever the last line is. And
I
then
think
also
Rust, yeah.
most languages, if you use a lambda, you don't have to specify the return keyword. It's just if you want to do more than one thing per line. So like, it's funny because all the object-oriented languages, or I guess you call them imperative languages because you don't have to do object-oriented in them, but they're all moving towards functional. And so that kind of just goes to show that like functional is that next level of abstraction.
Yeah. Here, as an example, you use a lambda keyword in Python, and you say like, "Here's my expression," right? You don't need to say, like, if we click on this, we don't need to say return. This is just like what that's the point of a function is to return a result. So it's like I don't get why it's there.
But return is used for imperative styling.
Yes,
right?
yeah.
That's
but
why, because you can have multiple lines per code. You can return early. Like there's a
Right.
lot of which is not
Right.
it's not great. Like it's better to have your functions just have a single return and to treat them like expressions.
Right. Like, because I mean,
Especially if you have a function that has like 5 return statements inside of the function. Like it's so hard to wrap your head around that as someone who's coming to read it for the first time. So
right. Forgetting how to write it in Python, but like, for example, to elaborate on what Kyle's saying, you could have a while loop that's like, um, um, you know, like, I'm trying to think.
what are you trying to do?
I'm trying to like, I was gonna basically say like if we have a value here, and like and we do some logic to like implement this or like increment this.
It'd have to be outside of the while.
I'm mixing languages together here, but the point I'm trying to get to, I'm not trying to spend too much time on this, is just like that if x is x modulo 12 equals 0, and we have some logic to increment this x, then we would just say we would just be able to arbitrarily say like return x, and then that's how we would write it in object-oriented programming. And I guess like that would be
Then
the
below
reason.
it, you could say return x plus 1, for example.
Right. Yeah. If
Or like you don't need to type it out, just type in return x plus 1
true.
outside
Oh,
of
okay.
it.
Gotcha. Yeah. Like in that case. Okay.
So like this is a valid function, but like it's not safe. Like we would discourage you from writing functions like this, which is why we move over to functional programming, is because we want to treat our functions as pure expressions as opposed to like, well, in this case it does this, and in this case it does that. That can become like, I mean, in this case it's simple to understand, but when you get into writing functions that are a couple hundred lines long, or even if you take that 100-line long function and split it into 5 different functions, it's still extremely complex. And it doesn't stop you from manipulating state between those 2 return statements. So
Yeah.
you could add something in the future that makes one of these return cases never hit or hit all the time. And so, yeah, we never want to write code in the future that's going to impact our previous code.
Right. And even too, it's just hard to reason about like if if I'm coming in and this is someone else's code, and I can see that there's like 2 different cases in which it's going to exit. It's just simply harder to reason about, and it's going to take me more time to figure out what it is it's doing and why I got the particular result I did out of it.
Yeah, so I think That's good.
Yeah.
Is there anything else you want to do for functions before we go to type classes and then try to get to the state question from Nick?
Sure. Yeah. The last. Yeah. Oh, right. Okay. So, um, last thing. Sort of like, let's take this and make this like a little bit more abstract, just to show like what exists in a function. Um, so we know that we have like okay, we have our number of arguments and then some output. The other component or syntax to a function that exists is the type classes. So we have this special arrow here, this equals arrow, and this just puts constraints on um, the following type signature. So this num a means that the num that a must be an instance of num, and that it must be the same. Sorry, no, I'm getting ahead of myself here. All this means is that a must be an instance of num, and so we see this applies to two different variables here. So both of these must be num. The same would be true if so like this and this are slightly different. This also implicitly means that a must be the same type as the other one, right? The input type must be the same as the output type. But let's say that's not true. There's another way we could do this, which is we say we have another type constraint here, which is that it must be a num on the input and a num on the output, even though the types themselves could be different. And so that's the syntax of functions there. And the last thing I need to show here is just how to pattern match on this, and then I'll only do it for like the case statement, because I think we'll see more organically how to do it with guards, and in the function that is not even recommended. It is a way, but you know what? We want to get to overloaded functions anyways. So let's do this. So let's say
Our previous example has implemented guards, so you can take a look at the example from last session to see how guards work. It's quite similar to this.
yeah. So guards are a lot more flexible. Why I want to get into case statements here is because what you'll see is that this case statement very deeply relates to the data definition. So I'm just gonna get rid of this. I'm even gonna pull this down here just so we see it like literally right in front of our faces. So if we know that our input type is something of instructor's car bool integer, what cases could we have here? If we know our data types and how we know how our functions work, we know that there's three cases here. And the three cases must be the data constructor Lauren with some L here. I'm just gonna put like a hole there for now, so I don't have to think about it. And then we have Kyle with a B. You don't have to call it B. You can call this whatever. We're defining the variable here, like we're pattern matching and defining that B. And same with here. I'm just gonna say actually G instead to make that point. So we have three cases here. And the reason we have three cases here is because it's directly because of the data type. So if we were to take out this case, bye Galen, then we would only see two cases here. And that's directly what it is. And this is like where the idea and term pattern matching comes from, right? Because these are patterns of the instructor's data type. And this is true whether or not we have these variables here, right? These don't have no impact on the pattern, on the idea of pattern matching. You know, they only affect the way or how we describe that case or of that pattern. So for example, if I took that out, then I would match it like that. Galen has nothing.
Can you show the what the compiler does here? Because I think that's extremely important. And like what would happen if you, for example, added a new case to instructors but didn't add a case to the function?
Okay, so this is so.
Maybe you have to implement the function first, but I think
So-
that's really important to showcase, because this is actually not possible in other languages.
Okay, so
I've tried so many times to get other languages to do this, and it's not possible.
yeah. Okay, so okay. I'm
Except for Rust. If you really want to do object-oriented programming, use Rust, because it uses Hindley-Milner type systems. But functional programming is better and faster.
I'm just gonna say undefined for now. This is like a literal function in Haskell, and you don't want to use this like in like production, obviously. But it's just it's helpful for like debugging certain things or thinking about certain things when you're getting used to stuff. So it's going to be a bunch of errors. Defined but not used. So I'm just going to say this to highlight this further. And this is something I want to make a good point on. I want to clarify, Kyle, what you're saying. It's not like actually an error. It's a warning, but you can make warnings an error.
And you should.
Yeah.
You should make this an error.
Right. Yeah. And it's a setting in your Cabal file that you just say, like you just convert. You can convert particular warnings to errors in your Cabal file, and I'll put how to do that. We have that for the ACE platform. We have so the ACE platform has literally 0 warnings. At one point, we had 1,500 warnings, but then we put in that clause that no warnings are allowed, and now we're down to 0. Yeah, so this is saying incomplete patterns. So this knows that you have not matched on Bobby. So the same thing is true. Like you might even be like, well, like that's like easy for a compiler to do. I mean, look at that. What about something more complex like integer? And integer like would be the same thing. We wouldn't have necessarily like a case statement for like each one where it's like 1, 2, or whatever. But we might have like particularly matched cases, and then we would have like a catch-all case like this to do whatever. And so like here, we can make this exhaustive. We can complete this by saying either catch all cases that we have not pattern matched on and do something with it, or we can just directly match on Bobby, and then we're good. So yeah, I'm gonna get rid of Bobby though. Did not make it through the hiring process, I suppose. And okay, so Lauren. So how do we now reason about this? And this is a little bit more challenging because we have to like rely on our type signatures here a bit. So I have to look at this like instructor's car bool integer and ask myself, what would Lauren have here? So we know that Lauren has the first type argument. So Lauren has a character. So I'm going to call this character. And Kyle has the second argument, which is a bool. So and Galen has the last argument, which is integer. And So now we have to we still have to work within the work within the constraints of our type system that we've set out, and we have to return it. We have to make this true. We have to make the output actually fit this type that we specified that it does. So I just do the same logic here. So I see that the first argument, which is given to Lauren, must be an integer. So, okay, so Lauren, I guess I'll just give her an arbitrary integer here. I'm just going to say Lauren 1, Kyle, Kyle is getting a car. Right. Okay. So Kyle's getting a car. So I'll put T for Tesla, and then Galen is getting a bool. So I just have to put a valid value of bool there. So I'm going to say Galen true, and that works. Now, are there other cases of this which are valid outputs as well? I have made it so that Lauren gives back Lauren, Kyle gives back Kyle, and Galen gives back Galen, because that seems like the most logical thing to do. However, if there's no reason I couldn't just completely get rid of Galen here and say Kyle T. Right? Kyle, the data constructor of Kyle still has to take a character based on the type signature, but there's no reason to say that I have to return this particular case. And so I just want to demonstrate that.
Sorry, Galen. You're no longer an instructor.
That's fair. I'll pack my bags and go home to where I already am. So that's that. And yeah, I guess too, just for the sake of exhaustion here, we could say that we could add in a type constraint here and make this instead num a, and this would be valid as well. I'm gonna say this I guess I'm gonna add this in as well, and this would be another valid way to write this idea. And I wonder, does this know? Yeah, define but not used. So again, we never use these, so it's saying why are you even defining them? Just get rid of them, and voila. So okay, that is everything to do with functions, right?
In the interest of time, I'm wondering if because I'd like to answer Nick's question if we can. There's 20 minutes, so do you want to try to take a stab at state, the monad question? Or
yes, but I do want to do it, but I definitely think that
because the overloaded functions type class is going to take you 20 minutes. So
Nick,
maybe
I'm not sure if anyone else is at understanding state T, unless
maybe we wait till next one for that then.
Let me get through overloaded functions first or type classes, and I don't think it will take 20 minutes.
Okay. All right.
I've kind of been giving the
3, 2, 1, go.
Okay, I've been giving all of the ground information to understanding type classes, and so this leads nicely into type classes. So what is num here? And I'm gonna change this out slightly. I'm gonna use a simpler type class called show. So now this just simply this still means the same thing roughly, that A and B must have instances of show. So what does that mean? Well, if we look at the syntax for show, for a data class in the context of show, we'll see that class show A, what we'll look up in the source code is class show A, where show is a function which takes an A and returns a string. So this is an overloaded class where whatever the A is must become a string. And if we look at this, if we look at the information around show, we'll see that there's like a ton of things which are showable. And we can see something too, that we don't have to have just one function here. We have like the function show list, which takes a list of A and turns it into a show S, which is like a kind of like a helper function, or sorry, helper data type to show, is how you can think of it. But we can see that we can do show for a car, show for an integer, an int, a bool, you know, almost anything, right? And we can do show on a list as long as the data type in that list also has a show instance. So what does this mean? Oh yeah. If I say show 5, okay, it's gonna say all that like jazz about like the type defaults. But let's say I say show true. It's gonna turn true into a string. So this is very simple. What we're doing here. Show is like you know, the simplest like sort of type class I can think of, and almost anything can be converted into a string, right? The same thing can be done with instructors. We could say, I'm actually going to just comment this out so we can see it here. We could say instance show instructors, right? So instructors is our data type. And we need to make sure that's a full data type, right? This is going to complain and give us an error about the kind signature. So I'm just going to say LBI to be quick. And if we say show, I'm going to do another way of pattern matching, which is show Lauren L. I'm going to say show Lauren and show Kyle K equals sorry, I don't need the show here because I'm just giving it back a string, so I'm just gonna say Kyle and then show Galen G is just Galen. So that's also valid. I don't even need to name these, so I'm just going to show that it takes an argument, and that's good. And I've written my instance of instructors, or show instructors. So now, like what's cool about Haskell, and I just want to show this quickly, is for a very simple class like show, we can usually just say deriving. So Haskell does this for us. Right, and it's gonna the actual definition is gonna be a bit different. It's gonna be different than this, but it'll be better. And I didn't want to do this manually for the sake of time. Oh yeah, okay. Oh yeah, that's fair. Sorry, I'm for the sake of time, I'm just gonna get rid of this. Cool. And so if we do show of instructors, or sorry, show of Kyle bool. Sorry, Kyle true. It's just gonna say Kyle true, right? So I don't know what this is. Ignore this for now. And yeah, that's exactly what's happening there. So that's using a type class, and we don't need to worry about like, if I say like then like instead, show Galen, um, E. It's also able to work with that data type. So show is able to work with a data type as long as it has an instance of itself. And we've seen that with bool, and we've seen that with car, and we've seen that with instructors, which is a more complex data type. And so that's data types in a nutshell. And we, yeah, but I don't know if there's anything more to say that with that is totally relevant. I mean, like there are so many different type classes you'll see in Haskell, and they're a beautiful way to create abstractions in Haskell, and there's really no limit to what you can do with them. And we'll see more examples of that as we go along. So again, not new classes. That's the last thing I need to say. But I think that sets us up for state T, right? Kyle, do you have any? Is there anything I've missed here?
No, I mean that's the simplest way to explain what a type class is.
Yeah.
Is it's really just allowing you to like almost like share functionality between similar types.
Right.
Right.
Because otherwise, I would need like show instructors, and then I would need, and this isn't going to work. Show car. Show, oh, that's actually a thing.
And I think what's it
it's
called?
not.
The default instances of these like make a lot of things really nice. Like I know with for example, just with like the JSON type class, like the to JSON and from JSON, those are super nice because it quite literally looks at like the name of your function and like creates a JSON object out of that. And like you don't actually have to you don't have to define how you want your JSON to look. It's able to understand based on the type system, like what you're probably asking for, and then you can further override that, right? So generic default type class instances, I think, are amazing.
Yeah, and the only thing I'll add to that is like, I think what's cool about this is like you don't need to know anything more than this. Like to do Haskell, you don't need to know anything more than what we've really talked about here. I mean, like the core understanding you need around types, like it is really here.
I would say if you want to write everything yourself, then yes. Where you might come into it's just you're gonna there's gonna be like say a library developer uses like a type family or something like that. You might need to know how to interface with it, but like you don't like this is I'd say like 90. No,
Yeah.
you never.
I never no like it's very rare. I mean, like yeah, there's is in theory a possible case. The point I'm trying to make here is that like when you're talking about JSON, right? The the like the power that exists in JSON is because of like the advanced Haskellers saying like, well, like what can we do with these basic types, and like what like how can we create a system knowing that this is like the full scope of like what basic types are. How can we turn this into like just like how can we use that understanding to create something awesome like an auto deriving JSON. And if you're interested in this, you want to look into something called generics in Haskell, and you'll see how it's possible to create functions which like interface with like just basic Haskell data types, and know how to create like a consistent representation. And I'm getting a little wordy here or whatever, but like it's the point I'm trying to make is that like by getting to this level with Haskell, you allow yourself to interface with like beautiful code that people who are in Haskell, who have been writing Haskell for 10 years, are outputting, right? So when someone's writing a library, like it's implicit that like they're trying to make it as easy to understand as possible. Hopefully, I mean, not always the case, but like a lot of like the best libraries in Haskell is like they're really trying to make it so that like here's a simple example to understand it, like JSON, for example. You know, where is it? Like this is, you know, it's really easy to read through this example here, and you know everything about it. But like there's so much like underlying work that has like gone into this, to make it so that like no matter what you are doing, this works perfectly, and it's really cool. And I just want to make that, I want to drill home that point. And you don't need to understand, like, right, you don't need to understand like how data.ason uses generics, right? But you're able, without understanding that fully, you can easily interface with Haskell. And the real reason I want to make that point is because like that's how it should be. I should never need to go into a code base, and I shouldn't, like, there's not a good reason, there's not a good like design reason why I should have to read every single line of code to understand something perfectly, or like at least to a certain level. For example, like with this function here, like in general for a Haskell function, you know, I'll have like a comment here saying like this function does blah, or you know, and hopefully it's a really good explanation, of course. But like out of like these, like, what is this, like I don't know why I can't think right now, like 6 lines, I should not need to read these 4. Like great Haskellers will tell you, like, you should not need to read these 4 lines to know what the function does, right? There's a real like almost like API separation between like this, like the type signature and the comment, versus the function body. And so like what this means is 2 things. Is like, assuming I'm following this like to a T, and I'm really believing in that statement, I can write my function body however I want to, and as long as it like makes sense to me. I mean, you know, I should be careful with how I'm saying this, like, because this could be misinterpreted. You know, I could use some really advanced Haskell to write this very succinctly. You know, that's one way I could do it, or I could write it very verbosely, like I'm doing so here. But it doesn't matter, because I should be able to show you what it does based on the type signature and the comment, right? And like for any given case in here, there's a lot of instances here. You know, maybe I shouldn't go into this or whatever, because this will get a little bit more complex. But like, you know, list to JSON, like, or sorry, lift to JSON, parse JSON to like this. I mean, there's a bit more like complicated types that we have here, but ultimately, I myself can like definitely reason about what it is this is doing here. Assuming that I know what the value data type is, assuming I know what parser is, and I don't need to. I never needed to read through the source code to see to understand what it is and what it does for me. And again, like, because of the Haskell type signature, I know that it actually provides me that type as it's specified. There's no case in which I could have a bug that this function says it's giving me back like a list or whatever, but then it ends up always giving me back a non-empty list. And technically that's true. You could do that in Haskell, but there is even like the concept of like a non-empty list in Haskell. There's so many ways to use the type system and to use types and insurers to ensure that like stuff just works as expected, right? Stuff just works as expected, and it's understandable and approachable for someone who doesn't understand your source code. So that's a bit of a rant I went on there, but any questions? Feel free to ask. That's the core of what we talked about today. So and let's go through